In the second section of Chapter 9, we're going to be looking more in depth on our quadratic functions and more specifically how to graph them. I'm going to skip over most of that first question. It's there for the answer in case you want to look over it. But I just want to look at these graphs down below it and show what happens when we affect one value from our quadratic function being ax squared plus bx plus c, and seeing what happens if I affect that middle term, so if I affect that middle coefficient b in that equation, see what happens to our actual graphs and our function. So notice that these three equations at the top, only one thing's changing on all three, is again that middle coefficient. So if I change from a 2 to a 4 to a 6, it looks like the actual function, if I was to put that into a graphing calculator and have it show me the graph, it looks like the function would just kind of shift over to the left and also to the down a little bit as well. But that important difference is that we could find out where that axis of symmetry is changing every time. In the first situation, it would be -1/2 where I have that dotted line. X is -1, dotted line axis of symmetry on the second graph, and that goes to -1.5 or -3/2 on the last one, and that's just, again, from changing that middle coefficient. So that's going to be important in terms of how we're going to find that axis of symmetry. It's also going to be how we're going to end up graphing those. And there's a way that we can reason through where this formula is going to be coming from. But the one big formula I want you guys to focus on that first page is more or less memorizing this. X equals -b/2a, where b and a are still coming from that same function. And we're going to look at it again on the next page. Again, if I'm given that graph, quadratic function ax squared plus bx plus c, if I remember that trick, x equals -b/2a, that exact value, that's always going to tell me where my axis of symmetry is going to run through that graph. Again, x equals just means it's a vertical equation because we always have a vertical axis of symmetry for our parabolas. And if I can find out where that vertical line is going to go, I know where I'm going to create some symmetry and make this a little bit easier to graph. So where that line comes from is, again, b and a from your function, and that's going to be the first two terms. Third term is still important, so the y-intercept, c, kind of like it was in your y equals mx plus b equations, that number at the very end is still going to tell you where your y-intercept are. So first two, those numbers are going to tell us where to put our symmetry. Last numbers are still going to tell us where the intercept is, and if I use both axis of symmetry and that y-intercept, that's going to help graph it. So really only one big question to focus on, and this next one that we're going to do, is how to graph these. And that's, again, starting from your quadratic function, ax squared, bx, and a c. So I started us off with that last definition. Again, this is the one big formula you're going to have to be using in your homework problems, x equals -b/2a. Only thing I have to do to find that axis of symmetry is plug those parts in. Looks like our b term is just -6, so I got to remember to plug in with the negative. Negative b is a -6 because my b term was already -6. And then 2a might be tricky on that one, but if I just have x squared, that means that there's basically an invisible 1 in front. So my a term is just going to end up being 1 once I plug that in. And we still want to simplify it. We still want to make the easiest line possible. So -6 would change that back to a positive. 2 times 1 is 2. And if I simplify that down to just get 3, now I know this line, x equals 3, is going to be where the symmetry is on my graph. And we could even start our graph with that. If I wanted to graph this function, I know that x equals 3 is really just describing a vertical line running right through that 3 coordinate for your x. So if I know that this is my axis of symmetry, again, technically this isn't my parabola. My parabola is going to be some kind of U-shape that we're fitting on this graph. It's not going to be that one. But we at least know that this line is going to be where the symmetry is reflected. So really all that's left is to find the actual shape of that function. Now that I know where the symmetry is, I'm going to use that symmetry to help graph it. And you guys are going to be getting comfortable with your tables of values again. If I want to take any x and plug it into the function that I had from the question, I should be able to find out what it simplifies to, and that would be my y value. So the first value we always want to test is we always want to test that axis of symmetry. So if I know that the axis of symmetry was running through 3, I want to take 3 for x and just plug it back into my equation. So if I plug that in as 3 squared minus 6 times 3 plus 4. Again, you could use your calculator for this. You could multiply it out. But I think if I get 9 minus 18 is -9, plus 4 more is -5. And that tells me that by plugging in 3 and getting -5 back as a result, the point on my graph would go at 3, -5. And again, since that was on the axis of symmetry, 3, -5 would be 1, 2, 3, 4, 5, if I can count. Looks like down here. What we always know about our axis of symmetry is the only point that's on that graph, it looks like the one that we just made, is going to be what ends up being the vertex. So our vertex is going to be that point that we found, 3, -5. We always want to start our graphs from there because then we can just use our symmetry. And the reason we're saying that we can use the y-intercept is that it's pretty easy to plug in. I know that if I'm looking for the y-intercept, the x value is going to always be 0 because I'm just on that y line itself. So if I plug 0 into my function, it's a pretty fast one to check even without a calculator. So if I do 0 squared, that's 0. 6 times 0 doesn't change anything. Only thing I need for that y-intercept is that last value. So my y-intercept, without even plugging it in, we could already tell just by looking, is just going to be a positive 4. So that tells me another part of my graph. I know that 0, 4 is a point on my parabola. That means I can go up to 1, 2, 3, 4. This is going to be a spot where I can use to help make my shape. And what we know about the last section is I can also use symmetry. If 0, 4 is a point on the parabola, so will this point somewhere over here on the other side. We just want to count over and make sure it's the same distance. So 1, 2, 3 on the left. If I do that same distance on the right, 1, 2, 3, it looks like this point over here is also going to be on my parabola. And I think that's the point 6, 4. Again, we're not even really plugging that into our function. We're just using our symmetry to find that. So what we do have is 3 points. What I would ask though is that we have a total of 5. Only thing you're going to need to do there is just plug in some other point to figure out our shape. So let's say if I just take another easy point, let's say if I plug in x equals 1, we want to find out where the point's going to go somewhere in that area. That's usually a pretty easy one to test too. So x is equal to 1. Again, if I just plug that in, 1 squared minus 6 times 1 plus 4. Should be pretty easy to find. I think 1 minus 6 is -5, plus 4 more is -1. So after I plug that point in, plug in 1 for x and get -1 back for y, that's going to tell me again another point to plug in on my graph. 1, -1 would be this point right here. And just like what we did for the y-intercept, we can also reflect this point and get another point on the other side. What I'm always going to ask for this is that we have 5 total points. So I think this is at 5, -1, where I just made that point. That would give me a good shape for the actual function. Only thing left is to draw that U shape through that as best we can. As long as we have those 5 points labeled, that would be enough for credit. So really, again, only 2 things to look out for. We need to look that function up, x equals -b over 2a, plug the pieces in from your function, and once I have that starting point, if I know where my symmetry is, I can start with my axis of symmetry, plug that point in to find out where the vertex is, and then using the y-intercept as one easy point to plug in and just choosing your own for the last one to finish with, that would give us the shape of our graph. And this one off to the right, hopefully you can give that a shot and get it correct by yourself, but let's look at that answer now. Again, all I did was I used that same function, -b over 2a, plugging in those pieces from the actual equation themselves gave me an axis of symmetry of 2. And if I know that that's where my symmetry is, I can start there from my table and find out where the vertex is. If I plug 2 into that function, I think I also get 2 in return, and that again is the coordinates of our vertex. 2, 2 is where I can start my graph. Using the y-intercept as an easy point to plug in, we know the y-intercept's at -2, reflect that point over, and to finish, I can just choose any other point. It just so happens I choose 1 again. It doesn't really matter what you choose as long as it's easy to solve. Plug 1 into that function, I think I also get 1 again as an answer. So if 1, 1 is a point, so will that point that's being reflected. Use those 5 points to make your U shape. So one other type of question we're going to have here is basically figuring these same parts out from a word problem. And this is not going to be really a formula you guys have to memorize. I'm just using that kind of model to create an equation for our next situation. And in that model, there's basically going to be a couple of things we're looking at. Height, time, which would be t, initial velocity if I throw an object into the air, and c is basically where that object starts its flight from. So you guys can read through that paragraph, but we're really just condensing it down to this sort of question. So let's say if I'm at a Ducks game, intermission, t-shirt launcher shooting into the crowd, starts off shooting from 5 feet above ice level. We want to figure out if I shoot a t-shirt at 64 feet per second, and I'm there to catch it 35 feet above the ice, a few different questions to answer. So first one is, how long will it take me to reach its maximum height? And maximum height, in terms of the path of an object, if I throw it into the air, the maximum height is really just another name for where does that vertex end up. The vertex is going to end up at some kind of time it takes to get there, and also some kind of height it ends up at the very top of its path. And that's going to be the next question. How far above the ice will it be? Really just a fancy way of asking us how to find vertex from this question. So if I'm using that equation, that were given from the last question, so negative 16t squared plus vt plus c. Really the only thing that we're plugging in is the initial velocity of 64 feet per second. That's how how fast I shoot that into the air. So for my function, I know it's going to be negative 16t squared plus 64t plus, and c would be your starting height, so that would be starting from 5 feet above the ice. And using that equation, again, if I'm trying to find the maximum height, how long it will take is by finding out that time variable, and time is kind of like how we used our axis of symmetry, is just going to be that same formula, negative b over 2a. So just practicing the same thing. B is going to be 64. If I plug in a, that was a negative 16. And if I simplify that, I think I get negative 32 here on the bottom. That just simplifies to 2. So same thing for my graph. If I was trying to find that point, the x value would be 2. In this case, it's just going to be the time coordinate. So it looks like it would take 2 seconds to reach max height, we'll just say the max, and that would be your vertex. And then how far above the ice will be basically how far is the height at that exact time. So kind of like what we did from before, if I take 2 and plug it in for t in my function, I just want to plug that value in and see what it ends up getting. So if I get negative 16 times 4 plus 128 plus 5, let's see, I think that's negative 64 plus 128 plus 5, ends up being 69 feet above the ground that's going to reach in terms of your ice level. So if it's 69 feet above the ground, that means there's actually one more question here to answer. What's the range of your function? We know that the 5 was the closest it's going to be to the ice when I launch it. It ends up at 69 feet above the ice, so you're limited between those two values. That's what we can answer for a range.